The following is an original production of AZPM News.
Arizona Science is supported by Research Corporation for Science Advancement.
For Arizona Public Media, I'm Tim Swindle, Professor Emeritus of Planetary Science at the University of Arizona, and this is Arizona Science. Joining me today is Bill Hubbard, also a Professor Emeritus of Planetary Science. Welcome, Bill.
Thank you.
Bill, you've been deeply involved with the Juno spacecraft that's been orbiting Jupiter for nearly 10 years. What have been the most significant things that we've learned from Juno, from your perspective?
Probably the most significant aspect of the mission to me is the very precise measurements we've obtained of Jupiter's gravity field. It's not a spherical planet. It has a lot of complexity in its gravitational potential. Some of those variations are time variable. Some of them are not. The planet is also precessing. It has a lot of interior information in all of this data, and we're still working on trying to understand what it's telling us.
Why is it not a spherical planet?
It is a rotating planet. It rotates pretty fast. It has a rotation period of around 10 hours, and it spins much more rapidly than the Earth does. And you can see that if you're looking at it through a telescope. You can actually see it rotate if you look at it over the period of a few hours at night. It is therefore distorted because the gravity is different at the equator than it is at the pole.
And you mentioned that the gravity field contains information about the interior. How do you find out something about the interior of something that big, that far away?
We had sort of a standard model of Jupiter we'd been using for years. We plugged it into this theory, which we had tuned to produce results that were as precise as Juno was going to give us. And then when Juno measured the actual gravity field, it didn't fit.
Any idea what's going on that's different?
One of the key elements in this is what's called the equation of state, which is how hydrogen, Jupiter, by the way, is mostly hydrogen, how hydrogen compresses as you compress it beyond 1 million atmospheric pressures. This has only been measured by a relatively small number of groups who are able to get data in that range. Typically, it's data that comes from weapons laboratories because they're interested in how hydrogen behaves at these pressures.
What's next for Juno?
Juno is in what's called Extended Mission 2, actually. It was given an extension a couple of years ago to complete orbits that were not in the originally proposed mission profile. What this extended mission is giving us is the opportunity to observe what happens when Juno goes behind Jupiter as seen from the Earth. Those orbits were not doing that until the extended period. Now it's going behind Jupiter regularly, essentially every orbit, and the orbits are of the order of a month long. And we're getting gradually more and more coverage of the shape of Jupiter, the actual shape as measured by when the spacecraft signal goes out behind Jupiter. We're making those measurements over a variety of latitudes now, and the first big paper came out, which gave us some surprises there. Some things were expected, some things were, again, unexpected.
Juno has been in orbit around Jupiter for nearly 10 years and launched 5 years before that. How long before that was the mission in the planning stages?
I first started focusing on Juno after I had been involved with some unsuccessful Discovery class missions. I worked with some people at JPL. We proposed a mission called Inside Jupiter a couple of times. Inside Jupiter was beaten by some really good missions. For example, Kepler was one of the missions that beat us, and I don't feel bad about that. I think it's been an excellent mission. But we then put together a larger team to go for what's called a New Frontiers class mission, which was a much larger mission in terms of its scope and in terms of its funding. And so working with Scott Bolton, who was at JPL at the time, he's now at Southwest Research Institute in San Antonio, but Scott put together a team of people who had been sort of unsuccessful Jupiter orbiter proposers, and we thought, well, we've got to have a Jupiter orbiter. Surely that's got to be something we need to do. And so we put together a pretty good proposal, and we got support for that. It's been a long process for my career.
Well, 25 years is a long time to be involved with a mission. You've actually been working on spacecraft studying Jupiter much longer than that, haven't you?
When I first came to Arizona, I came here in '73, and the Pioneer missions were about to fly by Jupiter. There were two Pioneers, Pioneers 10 and 11. One of them went on to Saturn, actually. They were much more primitive spacecraft than subsequent spacecraft, but they had an opportunity to go behind Jupiter and let Jupiter go between the spacecraft radio signal coming from the spacecraft and the Earth. The initial papers were crazy. They were the JPL group that were analyzing the Pioneer radio signals were getting atmospheric temperatures that nobody believed. They were hundreds of degrees hotter than anybody had a right to expect. But they were the first measurements, so maybe they were right. Don Hunton, who was at the time at Kitt Peak, just across from us at LPL, came over and gave a colloquium trying to tease out why these results were not right and what might possibly be done about doing a better job of analyzing them. And so Don and I put our heads together and we figured out what the problem was, and we were able to work with the JPL people, and the next analysis that came out had much more reasonable atmospheric temperature. So that was my first involvement with Jupiter's atmosphere.
How has the way we look at Jupiter or think about it changed in these 50 years? Is it at all the same?
It was interesting. When I first came here, Kuiper was still alive. In fact, Gerard Kuiper hired me, and we had some discussions about Jupiter. And he had he was a brilliant planetary scientist, but he had a kind of an old-fashioned view of Jupiter. His spectroscopic work showed an atmosphere which was very cold, much colder than the Earth's atmosphere. It was basically, he thought of Jupiter as a cryogenic planet. Basically solid phases of hydrogen and helium and all the way to the center, and told him, that's not the way thinking's going now. Astrophysicists are looking at Jupiter more in terms of star-like models. And in fact, a scientist also at LPL, Frank Lowe, had just discovered that Jupiter emitted more heat than it absorbed from the sun. And putting that piece of information together with some recent work that I had done on the interior of Jupiter showed that the only way you could get that kind of heat flow would be if Jupiter was much more star-like. It would be have a much hotter interior temperature. Central temperature probably much hotter than the surface of the sun. So this was a revolution in the study of Jupiter, as well as mythical objects at the time, which were known as brown dwarfs. And it turned out that a similar set of physical approaches could be used both to analyze the predicted properties of brown dwarfs, and they turned out that they could be used. One could use similar astrophysical approach to understand the interior of Jupiter as well as brown dwarfs.
What are our next steps in understanding Jupiter and planets like it?
It would be nice to have another probe. The original Galileo probe was a highly successful mission which gave us measurements of Jupiter's atmosphere. And it turns out that the atmosphere of Jupiter is very heterogeneous. It's not a nice layered onion-like atmosphere as we had originally thought. The Juno measurements have shown that Jupiter has these amazing ammonia convection columns that extend for hundreds of kilometers in altitude, and they're limited in latitude. There's not the nice layered ammonia cloud structure that was expected, and that's probably true of many other condensables as well. It turns out that the Galileo probe, as wonderful a job as it did, seems to have hit a rather anomalous region of the Jovian atmosphere. And we're still scratching our head. We don't know whether the compositions that it measured, as well done as they were, we don't know if they're typical of Jupiter.
You've been working with spacecraft with Jupiter for a long time, but you've done some work in some other interesting places about Jupiter as well, correct?
Yeah, everybody knows about Stanley Kubrick's movie Space Odyssey, which involves a voyage to Jupiter. Arthur C. Clarke, who wrote the original book that the movie is based on, had a sequel to that book. And it was a sequel in which a spacecraft returns to Jupiter to orbit Jupiter, but they discover that it's possible to turn Jupiter into a star. I worked at a Soviet research institute on the interior of Jovian planets, including Jupiter. And at first, things were kind of tense, and my hosts were a little leery of me, and I was a little leery of them. But after 6 months, you get to know people, and you feel comfortable with each other. And so as I was leaving, they said we're going to tell you something that we're not supposed to tell you, but we want you to know that this is going on. There's a project here in the Soviet Union to try to detonate Jupiter, and I thought about that a bit, and I thought, yeah, I know what they're talking about, because Jupiter has a component of its hydrogen is deuterium. And so when I came back to the U.S., I didn't want to talk to any U.S. government people about this. I thought, I didn't trust our government anymore. I trusted the Soviet government. So I decided to tell Gerard Kuiper. And so I had my last interview with Gerard Kuiper. He was about to go off to Mexico. He would die of a heart attack a couple of months later. He wanted to know how my trip had gone and so on. And I told him, I said, here's the thing that I heard just as I left. And when I told Gerard this, he said, oh, that's the sort of repugnant idea you hear coming from a totalitarian government. And anyway, it turned out later on there was a group of us here at Arizona. We calculated the evolution of Jupiter, including what happens to the deuterium. And it turns out that nothing happens to the deuterium in Jupiter. There's no way you can detonate it, but if you could go about 10 times higher in mass, then the deuterium would in fact fuse. It doesn't do it in a very spectacular fashion. It just sort of fizzles a little bit and then it's gone. But it turned out that this was not an illusion, that the Soviet scientists that I had talked to, they were working on something apparently was also involving the famous Soviet physicist Andrei Sakharov. He apparently was aware of this, and he talked to Arthur C. Clarke. And so if you read Arthur C. Clarke's second Odyssey book, this is where this idea comes from.
Thanks for talking with us, Bill.
Oh, you're welcome.
Our guest today has been Bill Hubbard, an expert on the planet Jupiter, who's most recently been working with data from the Juno spacecraft mission. This is Tim Swindle, and you have been listening to Arizona Science. You can also hear more of this conversation and others on our Arizona Science segments by going to the AZPM podcasts at azpm.org.
Thank you to Research Corporation for Science Advancement for their support of Arizona Science.
This has been an original production of AZPM News.